Hello, everybody. We're going to talk about particle physics today. Let's get going. So, to start off, what is matter? I don't know. What's the matter with you? I don't know. Let's find out. Imagine you had a rock. It's kind of rocky to start, but imagine you had a rock. Now, a rock is made of matter, right? Yeah, I think so. Well, let's say we cut that rock into a smaller rock. Well, it would look something like this. We got a smaller rock now. We could imagine cutting all those little rocks into smaller rocks and smaller rocks yet, and eventually you get sand. Look at Sandy. Sandy cheeks. Hello, Sandy. But you can imagine eventually we would get something that would look like this. Here's a typical model of an atom. We're going to look at a lithium atom here. So you can imagine like a center of the atom is a nucleus. We got electron here, electron here, electron here. That's all fine and dandy. We all probably learned this in chemistry class, what atoms look like. Or do they? They don't look like this at all. This is just a model of an atom. It turns out that it's completely bogus. We shouldn't say that technically because it is very useful in a lot of ways, but this model of the atom is not 100% correct. In fact, it should look something like this. It's a little bit better representation because, my friends, this is where things get crazy. Matter is made of waves. Matter is waves. Oh my goodness, that's crazy. How can matter be waves? What's going on here? That can't be true. So let's talk more about this. You can imagine if this is an atom, let's say the nucleus is in the middle, you can imagine an electron going around and around and around in a wave-like pattern. If you go back to that diagram, you probably learned somewhere that electron, the first orbital can fill 2 electrons, and the next orbital can fill like 8. And then if you like energy level, I guess, and then different orbitals can fill 2 and stuff. Well, the question is, why is that? Well, it's because matter is waves. You can think about only certain wavelengths will fit into that area, that space. We call that matter-wave duality a quanta. A quanta is what we call it. So you can imagine a quanta looks something like this, whereas like a set wavelength, this could be like an electron, where it's kind of spread out through space, which is not like any one point particle. It's a kind of like a wave function. It's a particle wave. A particle wave. Quanta is what we call those particle wave dualities. Interesting enough that energy levels depend on the energy and the size of that quanta. We'll talk more about that later. But anyway, the way that this was figured out is basically the double slit experiment. You shine light through a double slit and it produces this wave pattern. Well, it turns out if you shine atoms and electrons through a double slit, it also produces a wave pattern. What? A wave pattern. Interference patterns are produced by atoms, by matter, by insanely, like, it's crazy. Waves, particles, the same thing. Oh, what is going on here? So matter is waves. It's insane. There's a fellow by the name of Heisenberg, scientist. He developed kind of a visual. He did a lot of research with this, but here's a visual that he came up with as well. Imagine you had a water, not a water, because you can't have a water. It's kind of weird. But you imagine a pail of water, and you poured it all over the place. But before you did that, you put one speck of dust inside the water, inside the bucket of water. Now that speck of dust represented by this, maybe the arrow here, little crossbar here. Let's go to present mode so you can see this whole thing. So let's say that my little arrow is this speck of dust. There's a speck of dust in the bucket, and if I poured this water out with the speck of dust in it, well, the speck of dust could bounce around, and eventually it's going to end up in one of these little puddles, or maybe the big puddle. We don't know. Well, that speck of dust is basically the electron. We can think of that speck of dust as an example of, like, this is an analogy, the electron. So where is that electron located? Is it located in the center? No, it might be. Is it located right here? It might be. It might be over here. It might be over here. It might be over here. There's a chance. There's a probability. There's a chance that it could be located any one of those spots. And it turns out that those chances are kind of defined by this model. There's a chance that the electron will be in this orbit, in this orbit, in the next orbit. Maybe it's here in the orbit. Maybe it's here in the orbit. Maybe it's here in the orbit. We don't know. It's all based on probability. Same with this one. It's all based on probability. Is the electron in the middle? Is it on the outside? But it turns out since matter is both waves and particles, it's really interesting because when Heisenberg said, and what it shows with Heisenberg uncertainty principle, is sometimes the electron is here, but when you look at it, it jumps over here. And then when you look at that, it jumps over here. Like instantaneously, it jumps over here, jumps over there. So his uncertainty principle says, hey, I can know the position of an electron if I treat it like a particle, but there's nothing else I can determine about it. I can't determine its energy, I can't determine its speed, I can't determine its velocity, I can't determine its momentum. So in order to do that, I have to think of it as a wave. I can figure out the wave's speed, I can figure out the wave's momentum, I can figure out the wave's energy, but I have to treat the electron like a wave then. Interesting enough. So electrons behave like particles and waves. Interesting. So if you want to know the position of the electron, you treat it like a particle. If you want to know the speed or anything else about it, you treat it like a wave. Because basically, it's here, now it's here, now it's here, now it's here, now it's here. Well, I know its position at any given time, but how fast is it going? How much energy does it have? Well, that's when you look at wave phenomenon. You can imagine a wave. I know the energy, the speed of this wave, and since this electron is kind of propagating through space, I can figure stuff like that out. Like its wavelength, for example. So there's a guy named Schrödinger who developed an idea that kind of also an analogy to this scenario. Imagine you had a cat. You had a cat inside of a box. And at any given moment inside that box, there'd be a vase filled with poison that would break at any given time. And then the poison would kill the cat. So if you looked inside the box, you would know if the cat was dead or alive. There's no other detection to figure out if the cat's dead or alive. This is a soundproof box. You don't know if the vase is broke or not. The only way by knowing the cat is dead or alive is by looking inside the box. So when you look inside the box, the cat's dead. Look inside the box, the cat's alive. Well, the cat being dead could represent atoms and matter being like waves. The cat being alive could be the other way around. It could be particles. So until you look, when you don't look, the cat can be thought of as dead and alive. It's both. Both are equally probable, and both can be occurring at the same time conceptually. Only one of them is true, and until you look at it, that's when you know. Just like the electron, when I look at its position, I can think of it like a particle. But when I look at its speed, it behaves like a wave. So here's a kind of funny one. Wanted dead and alive, Schrödinger's cat. Not or, and. Huh. So we can actually figure out the wavelengths of different properties of matter. So it's the Broglie wavelength is the concept. Basically, every single thing in the universe, every object in the universe also has a wavelength. Most of the wavelengths are really small that we can't see them. In fact, you and me both have wavelengths. And the equation for this is wavelength lambda equals h, which is a constant. It's Planck's constant. It's 6.626 times 10 to the minus 34. Very, very small number divided by the momentum of the object. So you can imagine if I was running at 2 meters per second, walking, I guess that would be, my mass times my velocity would be my momentum. My wavelengths would be something along the lines of, just calculating that out, it'd be close to maybe 10 to the minus 37 meters. So my wavelength is very small, very, very small. So small we can't see it. Hence, why does it matter? Well, it's really cool because waves are awesome. Waves can pass through each other. Waves can be in multiple places at once. Waves can do a bunch of cool things. So if we're waves, we should be able to do a bunch of cool things. And waves are energy transformation. So we'll talk about that later. But anyway, so we're going to end with a joke here. Heisenberg and Schrödinger joke. So this is Heisenberg, this is Schrödinger. So imagine that they were riding in a car down the street and a police officer sees them and stops them, pulls them over. And the police officer says, hey, asks Heisenberg, hey, do you know how fast you were going? And Heisenberg says, no, but I could tell you exactly where I was. Ha 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 ha. Now the police officer thought, oh, this is kind of strange. That was a weird response. I'm going to search your trunk. So he looks inside the trunk and he noticed something strange. And he asks the two gentlemen, hey, do you have a dead cat in your trunk? And Schrödinger says, well, I do now. Kapach. Anyway, so what do we learn from this lesson? The key thing is that everything is waves and particles at the same time, or kind of, they could be treated as both, called quanta. And that, boom, 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 we can actually calculate matter's wavelength. Doesn't matter what it is. We can calculate its wavelength based on its momentum. So it's really interesting. So you can calculate the wavelengths of electrons. We can calculate the wavelengths of atoms. We can calculate the wavelengths of